Hi, this is Enrico Panontin and I will present the first spatially resolved measurements of the alpha-particle source in deuterium helium-3 plasmas at the Joint European Torus using the data collected with the gamma camera upgrade. This is the result of a wide collaboration under the frame of the JET experiment. Let's start describing the gamma camera upgrade. It's a system of 19 channels arranged in a 9x10 grid. Each detector has been recently upgraded with a lanthanum bromide crystal and a silicon photomultiplier. This upgrade resulted in an increased count-rate capability up to 1 megacount per second and a resolution of 5% at the cesium characteristic gamma ray peak. The gamma camera gives 19 integrated measurements, and from that we would like to reconstruct the local information about the plasma emissivity in the poloidal plane. This is the tomographic problem, which we solved using the maximum likelihood expectation maximization iterative method. To do so, we calculated a weight matrix W, implementing the full geometry of the gamma camera line of sight. Also, in order to deal with the sparsity of such matrix, the profile of the gamma camera were interpolated in order to create a virtual line of sight in between of two reals 1. Since the gamma camera perform measurements on only two projections, we need to add some magnetic information to perform a better inversion. This is done using a magnetic smoothing operator which perform an average over the projection of the flux surfaces on the poloidal plane. In this work we present the tomographic reconstruction of a shot in which the 3-ion scheme scenario for radio frequency heating has been studied. The plasma was composed by a mixture of deuterium and helium-3, and there was a minority composed by fast deuterium accelerated by NBI, which was the target of the radio frequency. The scheme for the heating is shown in picture A, while in picture B there is the time trace of the electron temperature as measured by the ECE diagnostic. You can see there are some instability in this plasma that gives rise to sawteeth in the signal, but there is a period of stability between 48.8 seconds and 50.4 seconds, which was used for the inversion. Also, if we compare picture C, the neutron rate as measured by the neutron yield monitor and the rate measured by the gamma camera, you see they are proportional. This means that the measurement by the gamma camera is dominated by a neutron background. If we isolate the gamma ray rate, picture D, you can see that both picture D and picture C shows a drop in the rate when TE shows the presence of an instability, if the time between two instabilities is long enough. So, the data of the gamma camera has been calibrated with a parabolic calibration. For the shot under consideration, a calibration based on the intrinsic radiation and an external source of cesium and barium has been performed. This calibration underestimates high energy beams, so a correction has been made by calibrating also the shoulder of the neutron background. However, for later shots, there is available a calibration at higher energies based on a source of americium beryllium. Let's have a closer look to the spectrum detected by the gamma camera, in blue in the picture, and the one detected by one of the radial spectrometers installed at JET, in green in the picture. As you can see, the data from the gamma camera are dominated by a neutron background below 10 megaelectronvolts, but above that threshold you can see the signal generated by the 17 megaelectronvolt gamma ray emitted in a minor branch of the deuterium-helium-3 fusion reactions. So a hard cut at 10 megaelectron-volts has been applied to all the calibrated channels in order to separate the gamma ray signal from the detected background. By applying the inversion method described before to these profiles, we can reconstruct the spatial distribution of the fusion reactions between deuterium and helium-3. This gives information about both the energy deposition site of the radio frequency heating and on the spatial distribution of the alpha particle source during the discharge. Here we have performed the reconstruction by scanning the parameter space in order to find an optimum between over-smoothing of the reconstruction and overfitting of the experimental data. This scan has been evaluated using a Kolmogorov test. In conclusion, the JET gamma camera upgrade has successfully operated in a C38 campaign and beyond. 17 megaelectron-volt gamma rays emitted by deuterium helium-3 fusion reactions have been detected during the 3-ion scheme scenario experiments. The high counting rate capability has allowed to appreciate the effects of plasma instabilities on the measured counting rate, both in the neutron background and in the gamma ray signal. It has been possible to reconstruct the alpha particle source from the measurements of the gamma camera, and an example has been shown in this work. Thank you for your attention.